Okay, so this one in the book goes across 2 pages, but it was the tetrahedral numbers, and what are those?
Those are created when you stack
Can you hold that edge now?
progressive triangular numbers on top of each other.
Okay.
So it's a little hard to see, but this tetrahedron is constructed. You have a triangle with side length 4. So you have 4 cubes on each edge on the bottom. And that would correspond to 4 plus 3 plus 2 plus 1, so the 4th triangular number.
Oh.
And you have the progressive ones on top of that.
Uh-huh.
And then you just add them up to create the tetrahedral numbers.
Yeah, and they had a really clever way of explaining this. So let's see if I can zoom in. And it may be just simply that talking through this portion in the book is the way to go. So why don't you... Would you rather write these out on the whiteboard or talk through them in the book?
We can talk through it in the book, I think.
Okay. All right.
So,
I'm pretty zoomed in there, so you go ahead and... All right. So how do they explain this? Why we get this sequence of 1, 4, 10, and 20? And I guess this is going to be the explanation that corresponds to the 20.
So, yeah. We have... I think this is actually the 5th triangular number.
Oh, is it? Okay, so this is going to be the 42? Okay, that's fine. Yeah, sorry.
So, we can see that it's a tetrahedral number by the way these numbers are written. We have 5 plus 4 plus 3 plus 2 plus 1. That corresponds to the 5th triangular number. And we have the 4th, 3rd, 2nd, and 1st on top of that.
Yeah, so we've got, you can think of the layer, the top layer being 1 cube, the next layer down is 1 plus 2, then 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4, 1 plus 2 plus 3 plus 4 plus 5. Alright?
And then you take this 3 more times, but you rotate it. You rotate the edge with the 5 on it.
Okay.
Once you put it in this corner, and then once you put it at the top.
Yep.
And when you add this up, you get all 7s.
Yeah, you sort of add up these triangles, these rotated triangles with numbers, and by what appears to be just absolute amazing magic.
You get, this is now corresponds to the 5th triangular number times 7.
Yeah, just totally wild.
So they represent in equations. So you have 3 times your tetrahedral number.
Uh-huh.
That equals this 5th triangular number times 7.
Yeah, what does the 1 plus 2 plus 3 plus 4 plus 5 correspond to in this diagram?
1, 2, 3, 4, and 5.
Yeah.
And that's all multiplied by 7.
Okay.
Then you change this to the sum of the triangular numbers, which we know a formula for.
Alright.
3 times that equals the triangular number, the nth triangular number, times n plus 2. And we saw that here because we are using the 5th triangular number, and we get 7. We're multiplying by 7.
Yeah, we get 5, like on the top we get 5 plus 1 plus 1. It's maybe an inch more work to show that you always get the same number, but it's not going to be that hard.
And then we see that the formula becomes 1/2 times n plus 1, and this comes from the formula for the nth triangular number.
Yep.
And you multiply by n plus 2 because of this. Since you multiplied by 3 at the beginning, you have to divide by 3 at the end.
Uh-huh.
And so that's where you're multiplying by a 6th, or you get n times n plus 1 times n plus 2 all over 6.
Okay, so for the 5th one we would get 1/6, 5 times 6
7.
times 7.
So it would be 35.
Yeah, 35. I think I said 42 before, so I canceled the wrong thing. So the 5th pyramid here would have 35 cubes.
Yep.
That's cool. That's a really just amazing geometric way to think about the numbers and then rotating the triangles. And that's cool. So what did you think about these 2 examples in the book?
I thought the first one was really neat. You sort of squashed down what you added on. I forget what they called it. They had a term for it. What you added onto the cubes, and it sort of magically almost became a hexagon.
Yeah.
And then the second one was really neat as well. By maybe coincidence, you get all the same numbers here in this when you add these three triangular tetrahedral numbers up.
Yeah.
That's pretty cool.
Yeah, it's really neat. It's yeah, you're right. It's sort of a coincidence, but it's also kind of. It turns out there's a really like clever way to look at the problem, and when you look at it that way, it sort of becomes crystal clear.
Yeah.
All right, good job, man.